Welcome to this HP Expert 1 presentation. In this video, we're going to look at the basics of routing. We'll look at the differences between distance vector and link state routing protocols, options such as poison reverse, count to infinity, triggered updates, and a number of other basic technologies used in routing. Routing protocols, advertise networks, and prevent loops. I'm going to explain the difference between routed versus routing protocols, look at static versus dynamic routing protocols, and then explain distance vector routing protocols such as RIP versus link state routing protocols such as OSPF. Let's get started. Let's start off by looking at the difference between routed and routing protocols. A routed protocol carries user information. Examples would be IP version 4, IP version 6, and in the old days, IPX. So when you use a higher layer protocol such as HTTP or FTP, that information is using lower layer protocols such as IP version 4 or IP version 6 to carry user information from one device to another. The addressing scheme is based on the protocol. So for example, IP version 4 uses a 32-bit IP address and IP version 6 uses a 128-bit IP address. Now, how do routers know where devices are in the network? You may have a device in the UK and another device in the US. How is traffic forwarded from one device to another? Now, it's important to realize that every router along the path between two devices makes an independent routing decision. The router needs to determine an outgoing interface to reach the destination IP address. To do that, routers communicate information about networks using routing protocols. They will then determine the best path to the destination IP address using criteria specific to the individual routing protocol. As an example, RIP uses hop count to determine the best path. OSPF uses bandwidth to determine the best path. So routing protocols are used to automatically advertise networks between routers. That is how routers learn about available networks. It's also important to note that if a router doesn't have a destination IP address in its routing table, it will drop unicast packets. So if it receives traffic going to an IP address of, let's say, 10.1.1.1, but that network is not in its routing table, it'll drop the packets because it doesn't know where to forward them. So in summary, routing protocols allow routers to learn about destination networks. That facilitates the exchange of routed information between devices. Routers can dynamically learn about networks in the topology and then make routing decisions based on different criteria such as bandwidth to determine the best path. They then simply choose an outgoing interface based on the routing table to send the traffic to the destination. So routed protocols include IP version 4 and IP version 6. These protocols are independent of one another. And to illustrate that, let's look at the simple topology. Are these routers able to ping each other? The answer is yes and no. Notice there's a problem in the IP version 4 address. These two interfaces are in different subnets, so they won't be able to ping each other using IP version 4. But in IP version 6, they are correctly configured in the same subnet, so they will be able to ping each other. The point is, what one routed protocol does is totally separate from another routed protocol. They act independently of each other and use different routing protocols. As an example, OSPF version 2 is the routing protocol used in IP version 4. OSPF version 3 is the routing protocol used in IP version 6. Different routed protocols use different routing protocols, and they act independently of each other. Even if one routed protocol is broken, the other one may still function. There are two main ways that routes get added to the routing table of routers. The first way is to use static routes, and the second way is dynamic routing protocols. Now with static routes, you as the administrator manually enter routes into the routing table. This has the advantage that there's no overhead on the network, in that there are no keeper lives or constant routing updates between routers. RIP, as an example, sends its entire routing table every 30 seconds. So when using static routes rather than routing protocols, that overhead is removed. However, there are major disadvantages to static routes. The first one is that the overhead is on you as the administrator to manually update the routing table when the topology changes. Static routes do not automatically take into account changes in the network. You as the administrator would have to manually adjust the routing table if a link went down. So the overhead is not on the network, the overhead is on you as the administrator. Static routes also do not scale when networks become large. The amount of work involved is too great. So the routers do not adjust to topology changes. However, that being said, these days there are ways to monitor IP addresses, for example, and to remove a route from the routing table if an IP address is no longer available. So it is possible to implement some dynamic options with static routes, but the overhead is still very large. Now, static routes are still used in a lot of networks. The most common example is the default static route. A default route basically tells your router, when you don't have a specific network in your routing table, point it to this device. And this would typically point to another router. So the gateway of last resort would be the router that you are pointing your default route to. This is used, for example, when connecting a home or small network to the internet. You're not going to run a protocol such as BGP to learn the entire internet routing table, because your router wouldn't be able to handle 480,000 routes or more, which is the size of the internet routing table. So a default route is a special type of static route, pointing your device to a gateway of last resort. Another advantage of a static route is that you determine explicitly where traffic flows. So rather than a routing protocol making the decision, you as the administrator have control. But the flip side of that is that you also have the burden of administrating the routing table. Dynamic routing protocols such as OSPF and RIP dynamically add or remove routes from the routing table. The major advantage here is there is automatic adjustment of the routing table based on topology changes or traffic changes in your network, rather than you manually having to adjust to a topology change. The routing protocols update, insert, or remove routes from the routing table. As soon as you enable a routing protocol such as OSPF, the routers will form neighbor relationships and exchange routes with one another. They will thus automatically learn about the networks available in the topology. Routers exchange information about routes using different methods, but for example, with OSPF, link state updates advertise routes that are available. This does put overhead on the network because additional traffic is sent so that the routers can communicate with one another. However, as a network grows, there's an exponential increase in the amount of work that would be required if static routes were used. So the advantage of dynamic routing protocols is that there's less overhead on administrators to maintain the routing table. And once again, dynamic routing protocols can adjust to changes in the topology. Routing protocols use different criteria to determine the best path to a destination. As an example, with static routes, the administrator would decide which path the traffic should take. With RIP, hop count is the determining factor or criteria, and with OSPF, bandwidth is the determining factor. We as humans do this all the time. When driving from point A to point B, we would determine the best path based on criteria such as the speed limit, the congestion on a highway or motorway, the amount of time that we have, and perhaps some other criteria. Essentially, you're working out the best route from A to B based on some criteria that's important to you. Typically, to get from A to B, in the shortest time possible. By the same token, in this topology, when traffic is sent from San Francisco to San Jose, which path would the traffic take? When using RIP, RIP doesn't take bandwidth into account. So if we had a network 10.1.1.0 in San Francisco and 10.1.2.0 in San Jose, RIP would take this path because the number of hops is less than going via New York. RIP will not go via New York, RIP will go directly. RIP, however, is not considering the bandwidth of the links. So even though there are fewer hops, it may be quicker to send the traffic via New York than directly. OSPF, on the other hand, takes bandwidth into account. So in this case, OSPF would send the traffic via New York because the link speeds are greater. OSPF is a more powerful routing protocol and makes better decisions because it takes bandwidth into account, whereas RIP doesn't. RIP simply looks at the number of hops from A to B. Now you may say that you wouldn't have a network configured in this way, but see this more as an analogy to explain how routing protocols determine the best path or best route to a destination. The moral of the story is different routing protocols have different criteria to determine the best path from A to B. OSPF once again looks at bandwidth, RIP doesn't. Some terms that you need to understand with regards to routing protocols include autonomous system, interior gateway protocols, and exterior gateway protocols, or internal gateway protocols, external gateway protocols. So the first term, AS, autonomous system, is a grouping of networks under a single administrative domain. In other words, the routers within autonomous system 1 are under the control of a group of people or a company. As an example, this may be Coke and this may be Pepsi. It's very unlikely that Coke are going to allow Pepsi to manage their network. They are separate autonomous systems under different people's control. Routers in the Coke autonomous system are under the control of Coca-Cola employees rather than Pepsi employees. It's a separate autonomous system. Now, various interior gateway protocols or IGPs can be used within an autonomous system. Two examples would be RIP and OSPF. EGPs or exterior gateway protocols are used between autonomous systems. The EGP that's in use today between autonomous systems is BGP. So if this was a company that needed to connect to the internet, they would, for example, connect using BGP to their ISP. Within their autonomous system, they may be using OSPF, but BGP is the protocol used between their AS and the ISP. They'll be learning about internet routes through BGP. Now, only very large companies generally run BGP, but ISPs, which carry routes of customers, will run BGP. So we could have an ISP on the left-hand side and an ISP on the right-hand side, and they will be running BGP between them, but internally running different routing protocols. So an example would be OSPF in Autonomous System 1 and ISIS, which is another IGP in Autonomous System 2. Now, autonomous systems are registered numbers in the same way as IP addresses when connecting to the internet. So before you can connect to the internet using BGP, you would register an autonomous system number. There are private AS numbers that can be used without registration. So within an autonomous system, you could use a private autonomous system or any number you like, as long as you're not connecting to the internet. But as soon as you connect to the internet, you need to use a publicly registered autonomous system number. Please note this doesn't apply when you're using static routes or have been allocated a private AS number by your ISP. But for very large networks or when running an ISP, the autonomous system numbers need to be registered. There are different types of paradigms or algorithms used by routing protocols. The first one is distance vector, also known as routing by rumor. Distance vector routing protocols will determine the direction and distance to a destination. The direction is also known as the vector, and the distance, such as hops, are determined to any destination in the network. RIP, as an example, uses hop count to determine the cost or distance of a remote network. The advantage of distance vector routing protocols is that they are very simple to configure. The major disadvantage of distance vector routing protocols is that they have very limited visibility. They only know what neighbors tell them. And that's where the concept of routing by rumor comes in. It's possible that routers learn incorrect information or make bad choices based on the information that they have received from their neighbors. Distance vector routing protocols use the Bellman-Ford algorithm to calculate paths. This requires that a router inform its neighbors of topology changes periodically, and in some cases when a change is detected in the network. RIP, as an example, will advertise its entire routing table every 30 seconds and will send triggered updates when there's a change in the topology. Distance vector means that routers advertise routes as a vector of the distance and direction. Direction is represented by the next hop address, and local exit interface, and distance uses a metric, once again such as hop count in RIP, to determine the cost of the route. It's important to understand that distance vector routing protocols do not have knowledge of the entire path to a destination. Hence, the term routing by rumor is often used because the routers are relying on information that they receive from other routers, and they themselves cannot determine if the information is actually valid or true. This can introduce instability and routing loops, and thus multiple features have been introduced to try and combat loops. And we'll look at some of those features in a moment. An example of features or mechanisms used to stop routing loops includes split horizon, poison reverse, and triggered updates. So to sum up, distance vector means that destination, let's say 10110, is a distance of 5 hops away in the direction of next hop router, router 2. That statement sums up essentially how distance vector routing protocols operate. The destination, 10110, is a distance of 5 hops away in the direction of router 2. An analogy that's often used to help with the understanding of distance vector routing protocols is that the information provided is comparable to the information available from a road sign. Link state routing protocols have a road map. A link state routing protocol cannot be fooled as easily into making bad routing decisions because it has a complete picture of the network. A road sign, which is used by distance vector routing protocols, would just say go left and the network is 5 hops away. However, link state routing protocols have a road map, which allows the router to see the path to the destination, and therefore it can make much better or more informed decisions about how to get to that destination network. The name link state means that each router originates information about itself, its directly connected links, and the state of those links. In other words, are they up or down? This information is then passed between all routers, and each router makes its own copy of that information, but doesn't change the information. That means that all routers end up sharing the same information within a network or area, and that's what's called a topological database. In OSPF, you can use a command such as display OSPF LSDB to see the link state database. That's identical on all routers in the area. So each router has identical information about the network, and each router can make independent decisions on how to calculate its best path. Link state routing protocols use an algorithm called SPF, or shortest path first, which was developed by E.W. Dijkstra and is a very powerful algorithm used by protocols such as OSPF and ISIS. Once again, link state routing protocols have better visibility of the network, and we'll talk more about link state in a moment. But essentially, each router has a copy of the topological database, which is all routes in the network or area. It uses the shortest path algorithm to determine the best path to every destination. It has much better visibility of the network than distance vector routing protocols. The disadvantage of link state routing protocols is that they are more difficult to configure. They require a hierarchical network topology where we have a backbone area of area 0 and multiple other areas. Link state routing protocols also require more memory because they maintain more tables. The SPF or shortest path algorithm can also be very processor intensive and thus require more processing power. Another very important concept when working with routing protocols is administrative distance, as it's known on devices running the provision operating system, or preference, as it's known on devices running the COMWare operating system. This is essentially the believability factor of a route. Who do you believe? When multiple routing protocols are running on a router, we need to decide which routing protocol we're going to believe. If OSPF says go left and RIP says go right, which way will the router send traffic? Left or right? In other words, what is the trustworthiness or believability of the routing information that the router is receiving? Now, here are some defaults that are well worth knowing. As an example, on provision devices, connected interfaces have an administrative distance of 0. On COMWare, the preference is 0. The lower the number, the more believable the routing information. A directly connected interface is known about by the local router because it's directly connected to that router and thus has the highest believability factor. Administrative distances or preferences are in the range 0 to 255, where once again lower numbers are more believable, higher numbers are less believable. A static route in provision has an administrative distance of 1. In COMWare, the preference is 60. OSPF, internal, autonomous system external, or not so stubby areas have an administrative distance of 110 in provision. In COMWare, internal OSPF routes have a preference of 10. Autonomous system external, not so stubby area routes have a preference of 150. Once again, the higher the number, the less believable. And this can cause problems. In Cisco and provision, these are the figures used for OSPF internal and static routes. Notice static routes are preferred over OSPF, whereas in COMWare, it's the other way around for internal OSPF routes. OSPF is preferred over static routes on COMWare devices. RIP on provision, administrative distance of 120. Preference on COMWare 100. Unknown 255. And there are other values for BGP as an example. The moral of the story is routing protocols with lower administrative distances are preferred over routing protocols with higher administrative distances. So let's look at some examples. In this example, the San Francisco router is learning about a network 10.0.0.0/8, both from RIP and OSPF. So San Jose is advertising that information via RIP, and New York is advertising that information via OSPF. So the San Francisco router is running both OSPF and RIP. Now in this example, let's use COMWare. The values for OSPF and RIP are as follows on devices running the COMWare operating system. So in this case, OSPF is preferred over RIP because the preference is lower or administrative distance is lower. So the first choice is to go via New York, and only if that path is broken is the alternate choice to go via San Jose. The route learnt from OSPF is deemed to be a better route because the administrative distance is lower. In other words, OSPF is more believable than RIP. However, let's expand on that example. Router 4 in this topology is learning about network 10.110/27 from router 1 using RIP, 10.100/16 via BGP from router 2, 10.0.0.0/8 via OSPF from router 3. I've put the administrative distances in brackets. These are provision values. So, administrative distance for OSPF is 110. BGP is 200. RIP is 120. Which way will traffic go if router 4 pings 10.111? Will it go via OSPF or BGP or RIP? Which path will be chosen? Now it's important to take note that the length of the route takes precedence over administrative distance. In other words, administrative distance is only used if multiple routing protocols are trying to put the same route into the routing table. On router 4, he's learning about 10.110/27, 10.100/16, and 10.000/8, and the router will see these as 3 different routes. So all 3 routes will end up in the routing table, but this route will be chosen because it has the longest match. So in other words, the ping will go via router 1 because that is the best match or longest match. However, if we go back to the previous example, notice in this case, OSPF was chosen above RIP because it's the same network. Notice 10.000/8. Thus, administrative distance or preference was taken into account. AD or preference is only used if multiple routing protocols are trying to put the same route into the routing table. In this example, the 3 routes are seen as 3 separate routes. All 3 routes are put into the routing table, and the routing decision is based on longest match or best match. Another concept to understand is the difference between classful routing protocols versus classless routing protocols. So firstly, classful routing protocols do not advertise the subnet mask in advertisements. So they will, for example, advertise 10.000, but the receiving router will not know whether this is 10.000/8 or 10.000/24. This causes a problem because, as an example, if I gave you an IP address of 10.1.1.1 and another of 10.1.2.1, are these 2 IP addresses on the same subnet? Well, that really depends on the mask. If it's a /8 mask, then yes, they are on the same subnet. But if the subnet mask is /24, then they're not on the same subnet. So how does the router know what the mask is? And this is where the routers make a major assumption. They assume consistency of mask. Now, making any kind of assumption can be dangerous, and in this case, the same applies. What routers do when they are running classful routing protocols is they assume that the update received is using the same subnet mask as the mask configured on the interface where the update was received. So if the router receives an update on an interface with a /24 mask, it assumes that that routing update uses a /24 mask. If the router receives an update on an interface using a /28 mask, it once again assumes that that update uses a /28. That can be very dangerous. Another downfall of classful routing protocols is that they summarize across classful boundaries. In other words, if a class A subnet is advertised across a class B subnet, that advertisement is automatically summarized. And I'll show you an example of that in a second. An example of a classful routing protocol would be RIP version 1. Today, you wouldn't want to use this. You'd want to use RIP version 2, as it supports variable length subnet masks, whereas a classful routing protocol like RIP version 1 doesn't. So here's a network to illustrate the problem of auto-summarization with classful routing protocols. In this topology, notice this is a class A network. This is class B, this is class B, and this is class A. On router 1, when moving from one class to another, automatic summarization takes place. So this network is advertised to router 2 as 10.0.0.0/8. In other words, class A network. By the same token, when router 3 advertises 10.1.2.0, it summarizes it as 10.0.0.0/8. So router 2 now believes that it has two paths to the same network. So if on router 2 you ping 10.1.1.1, you would have a failure, success, failure, success, failure. Why? Because it's sending one packet in each direction because it's load balancing. It believes it has two paths to the same network, whereas in actual fact it doesn't. So that's a problem with auto-summarization in class-full routing protocols. Today, we use classless routing protocols. Classless routing protocols don't have the same issues because they advertise the subnet mask. So they will advertise 10.0.0.0/24 or 10.0.0.0/30. They also support variable length subnet masks. In other words, you can use a /30 mask on a point-to-point link and a /24 mask on an Ethernet link. Variable lengths of subnet masks are supported. Auto-summarization does not take place on routing protocols such as OSPF. You have to manually summarize. So the advantage here is you have the ability to manually summarize rather than being forced to summarize across classful boundaries. OSPF, as an example, can summarize routes on ASBRs or Autonomous System Border Routers and ABRs or Area Border Routers. Examples of classless routing protocols include RIP version 2, OSPF, and ISIS. That concludes this first video looking at the basics of routing. In the second video, we're going to look at distance vector routing protocols in more detail and look at some of the mechanisms such as split horizon, poison reverse, and others that help combat routing loops. In the third video, we'll discuss link state routing protocols briefly. For more information, please go to hp.com/go/expert1.